I'm going to explain how we can build a indexed file in Pintos file system. In original Pintos, the file size is fixed when it is created. It is somewhat very limited. So in this project, we'll modify Pintos file system to change the file size dynamically, and maximum file size will be 8 megabyte. This is the files you're going to modify. So this is how we allocate the block when Pintos creates a file. When creating a file, say file A, it saves the start block address and length to the inode. And then when you create another file, again you save the start block address and length to the inode. So this is disk. This is disk. So, but in file system, we perform append very frequently. We append a block to the end of the existing file, append another file, and append another file. Okay, but in Pintos file system, we cannot do that in the current file system structure because a file is represented by the start address and the size. This means that all the blocks associated with the file should be placed at the consecutive region on the disk. Consecutive region. However, in this configuration, there is file A. However, there is if we want to extend the file, but the next address has been occupied already, so we cannot extend the file. So we have to fundamentally change the way the inode represent a file. After modification, you're going to modify the file structure in Pintos operating system. How? Let me show you. After modification, an inode is going to have a bunch of pointers, and each pointer will point to the data blocks. Okay. At the creation of the first file, you allocate 1, 2, 3, 4, 5, 6, 7, 8 blocks, and with 8 pointers. At the creation of the next file, file B, you create another file, and with 8 blocks, and there are 8 files. 8 pointers. And if you want to expand a file A, then you allocate another block wherever there is a free block, and set the 9th pointer point to the newly allocated block. Then we can extend the file. So that's what you are required to do. Okay, so let me go into the details a little bit. The seek operation, it changes the current offset of the file. Let's consider this case. This is the size of the current file. Let's say this is a 512 byte times 8 blocks. This is 4 kilobyte. So the current file size is a 4 kilobyte, but the application calls seek system core and sets it to 10 kilobyte, for example. Then current offset is 4 kilobytes. Oh, sorry, I think it's too large. Let's say it's 6 kilobytes. Okay, and then current offset pointer is updated to the position where there is no file blocks updated. Okay. So when you modify the file system operation, and when you modify the file to the indexed organization, you have to check. You have to modify the seek file system core also, and when the seek actually seeks beyond the size of the file. It does not change the file size, nor does it allocate the blocks, but it just updates the offset. And when a write is called and offset, and when the actually write is called, okay, at this position, this block is still free and it has not been allocated to any of the files, but offset is updated to this point. At this point, if you or application calls write system core, then it places a contents at this point and initializes the intermediate blocks that hasn't been accessed anyway with some initial value. Okay. This is called punch hole, and punch hole is initialized with the value 0. So this is very interesting part of the seek operation. There are 3 things to do. First, you have to modify the undiscounted structure, and then you have to modify the code that uses undiscounted. That includes changing file offset to the block address and creating a new inode and deleting an inode. And also you have to modify and create the function that handles extension of a file. Okay, so this is an undiscounted in current Pintos. So this is sector start address, and then this is length of the file. So in current Pintos, the file block file is represented by the start address and the length. So we are going to modify that. So we are going to modify the undiscounted structure for the file so that we can extend the file. So this is sample inode. In this inode, there are a number of direct index and the indirect block, and then double indirect block. So in the single direct block, okay, there are direct block entries number of direct pointers. So that points directly point to data blocks, and then indirect block points to the pointer block that points to the data block. The third one is double indirect block. So it points to the pointer block that points to the another pointer block, and then that points to the data blocks. So this is 2-level indirection. Okay, so this is the layout of this is the actual layout of the file that belongs to the single file. Because in Pintos, each block, each inode occupies a single block. So the inode can be very large. So we don't want to waste any of the space. So for that reason, we are going to allocate as many as direct pointers as possible. So here there are from 0 to 124. This is of course this is sample inode structure, sample inode. So if you want to use different idea for the file organization, you're welcome to use your own idea and implement it. Anyhow, there is 124 direct blocks, and then there is single indirect, and there is another double indirect. This is total number of pointers in the inode. Okay. So in the new inode structure, there is file length, and there is magic number, and then there is 126 pointers. This is total of 126 pointers. Okay. And then here, from here to here, there are 128 integers, and each integer is 4 byte. Though 128 integers times 4 byte is 512 byte. So here, a single inode, single on-disk inode occupies entire sector. Okay, and then next thing to do is compute the sector number from the file offset. So we have to compute, we should be able to compute the sector number from the file offset. So Pintos already defines a function block sector to byte, block sector t, this is the return value type of return value, and this is byte to sector. So it provides an offset and it returns the sector number associated for that offset. We have to change that. So this is a byte to sector function, and it converts the position to a sector number so that you have to change this function properly. And another function you have to change is the code for creating an inode. So there's a function called inode create. In inode create, you have to inode create function is supplied two parameters. First one is sector, and there is length. So sector is the location where the inode should be created, and the length is the size of the file when at the time it is created. So originally Pintos allocates contiguous blocks and save its start address. However, here now we modify the code of the block address, all blocks are located. It's simple. Okay, and then deleting an inode should be changed slightly. When we delete an inode, we have to deallocate the inode has. So we have to add block deallocating code at the inode clause, because this is inode, and then there are a bunch of pointers, and then there is a blocks associated. So when you delete an inode, you have to deallocate all these blocks. That means that you have to set the free block bitmap for these data blocks to 0. Now it's time to handle an extension of a file. When the file size changes, it allocates a new block and update a data block pointer in the inode. And then you have to fill the allocate blocks with 0. Okay, that's the basic steps you have to do. There's function inode write at. Okay, and then here, of course, we have to acquire appropriate locks, and then when you write beyond the size of the existing file, then you have to update some field. The next topic is subdirectory. Original Pintos has only root directory, but not the other subdirectories. So we'll implement the concept of subdirectory feature to make the file system more reasonable. And we will bring in the concept of hierarchical tree structure. This is the list of files you need to modify in the course of creating the subdirectory concept in the Pintos file system. Okay, so this is the structure of the directory in original Pintos. There is only root directory. There is only root directory, and so directory is flat. And root directory, of course, has inode. Okay, and then inode has the associated data block. And the data block has a directory entry. And every directory entry in Pintos file system is just a file. Okay, so file means it is a file name and inode number pair. Now, based upon these, it allocates a file inode, and then it contains a data block associated with the inode. Okay. Now we are going to change the concept of this flat directory structure into a hierarchical directory structure. So here the root directory can contain the file, a regular file, as well as another directory. That's the important part. Okay, so a directory contains a regular file as well as a directory file. The important thing is that when there's a concept of hierarchical directory structure, there is two pre-allocated directory entry in every directory structure, which is current directory and then parent directory. So let's look at the details. Let's say this is root directory, and then there is inode. Okay, and then inode points to the data blocks of the directory, and each of these are directory entries. Okay, directory entries may refer to the normal file or may refer to the another directory entries. Okay, and then in directory entries, the first two directory entries are reserved for the special purpose, the current directory and then parent directory. However, for the root directory, there is no parent directory, so it points to itself. So these are the data structures you are going to implement in realizing the hierarchical directory structure.